Our final speaker is Gianmarco Iodice. And he's from ARM. Get his slides up here. Gianmarco is a computer software engineer at ARM in the lovely town of Cambridge on massively parallel computing on GPUs. He's been working in the research area on GPU computing targeting real-time applications of computer vision. He's going to talk about how to use GEMM and FFTs to accelerate deep learning. I would imagine that'll be on ARM processors. So thank you and good luck.
Thank you very much for being here. Today with this talk, we are going to explore two numerical foundation stones as matrix multiplication and FFTR, which are used for a wide range of scientific algorithms, which find application as well in deep learning, in particular for solving the problem of convolution in convolutional neural network. For what concerns the computing platform used to carry out our performance analysis, we have used a development platform with an ARM Mali GPU by means of OpenCL. However, all the consideration that we are going to show will be completely general, and they find a potential application as well on architecture with vector capabilities. So let's start to see the contents of this talk. After a brief introduction about ARM, we are going to introduce a minimal background behind convolutional neural network, answering three main questions. The main part of this talk will show two approaches for solving the problem of convolution. One based on matrix multiplication, SGEMM, and the second one based on the FFT. The third and last part of this talk will emphasize the important aspect of limited numerical precision for convolutional neural network in order to have a significant speed up. As I said, I'd like to spend just 1 minute about ARM. ARM is a British multinational semiconductor and software design company with headquarters in Cambridge, UK. For what concerns the silicon IP designed by ARM, where ARM is a leader with its microprocessor, we can find different solutions for a wide range of markets, definitely from sensor to servers. In particular, we can find IPs for CPUs, which are now in over 90% of the smartphone markets. We can find IPs for GPUs, IPs for video processor and display processor. In this slide, I have reported two important numbers for us, 25 and 75. 25 because last year in 2015, we have celebrated the 25th anniversary. And 75 because in 25 years, our partners have shipped over 75 billion ARM-based devices all over the world. Let's start our study answering a first question. What is the main difference between a traditional machine learning used for ages in computer vision and the revolutionary and powerful convolutional neural network? In terms of high-level design, it doesn't change anything, because we still have the feature extraction, which extracts a piece of information which is used to solving a target problem. And we have the classifier, which in our case is a piece of software which uses the extracted feature in order, for instance, to detect or recognize a particular object. Moreover, for convolutional neural network, the classifier is a fully connected neural network that we have studied for decades. So the main difference between the traditional machine learning using the past for computer vision and convolutional neural network lies on the feature extraction. Because while in the past the feature extraction was fixed, it required a lot of effort by expertise, because for each specific problem, we had to find the best feature or the best set of features. Now the feature extraction is learned. In particular, the feature extraction is made up of several stages of nonlinear trainable feature, where the nonlinear trainable feature consists of a convolution operation, which is the classic convolution that we use, for instance, in image processing, followed by a nonlinear operator and a subsampling stage. What are the trainable parameters? Are the weights of the convolutions. With this presentation, we are going to limiting our study just to the inference problem. And we are going to study just one layer of this powerful architecture, which is the convolution layer. The second question that I'd like to answer is, why are we interested to study the convolution layer? Because it is the most computationally expensive layer of convolutional network. For instance, for the AlexNet architecture, which is one of the most used architecture for computer vision, over 90% of the time is spent there. The third question is, why don't we use the sliding window approach, as this problem has been widely solved in the past for image processing with a sliding window? Because for convolutional network, most of the time we have multiple input images. We have multiple convolution kernels to apply with different dimensions and shapes. We have multiple channels per image and kernel. So what we can infer? We can infer that it is difficult to have an highly optimized version of a sliding window. So for this reason, we are going to study two high-throughput alternatives as a matrix multiplication and the FFT. The first approach that we are going to study is based on the matrix multiplication, or SGEMM. Until now, I have used indistinctly these two terms, but do they mean the same thing? In few words, yes, even if SGEMM denotes a more general expression, which includes a matrix multiplication and the addition of the other matrix. For convolutional neural network, we used to refer to SGEMM because most of the time, after the convolution operation, we need to add a bias. However, reducing the convolution to a matrix multiplication is not an obvious solution. And in order to do that, we need to reshape our input image. In particular, we need to use a function called image-to-call, which stores in each row of the output image the necessary pixel for each kernel application, as we can see from the animation. As we can guess, this costs in terms of memory requirements, because between two consecutive kernel applications, we have an overlap, and then we have pixels duplication. In order to solve this problem, we have an important parameter to play on, which is called distride. Distride is the distance between two consecutive kernel applications. So play on this parameter, we can reduce the overlap between two consecutive kernel applications, and then we can reduce the pixel duplication. Once we have ready our matrix A, we are able to reduce our convolution to a matrix multiplication. Because if we had, for instance, a vector B, which stores the weights of a generic convolution that we want to apply, the multiplication between the matrix A and the vector B returns a vector C, which stores the pixels of the output image. But the powerful aspect between this approach is the easy way to do several convolution kernels in parallel on the same image. Because if instead of having a vector B, we had the matrix B, which now the matrix B stores for each column the weights of each convolution kernel that we want to apply, this time the multiplication between the matrix A and the matrix B returns a matrix C, where each column of the matrix C stores the pixels of each output images. However, in order to restore the output image structure, we need another function called call-to-image. Okay, let's see a very naive implementation for the matrix multiplication. The main computation behind the matrix multiplication is a dot product between a specific row of the matrix A and a specific column of the matrix B. In the naive implementation, we have each thread which computes a single element of the output matrix. But the main drawback behind this approach lies on the matrix B, because every time we need to load a value from the matrix B, we need to load those values from different rows, which is not cache-friendly because you can incur in a lot of cache misses. In order to overcome this problem, we can think to transpose our matrix B. So each column of the matrix B becomes a row in the transpose matrix. This ensures that every time we need to load a value from the matrix P, we are going to load the value in a consecutive fashion manner. But what is the speedup achievable? Nothing, just 1.1. Because with a naive implementation, we are going to dispatch a lot of threads, and we can incur in a lot of memory transfer between the external memory and the internal memory, which are the registers. So in order to solve this problem, we need to dispatch fewer threads, and we need to exploit better the vector capabilities of our architectures, if our architecture has SIMD, for instance, capabilities. Another approach is the following. So each thread now computes 1/4 elements of the output, for the output matrix. But as we can see from the animation, basically we can see the same problem of the naive implementation. So every time we need to load the values from the matrix P, we need to load these values from different rows. So it's not cache friendly. In order to solve this problem, we need to reshape our matrix P. But this time, instead of transposing the matrix P in a scalar manner, we are going to transpose matrix B in chunk of 1/4 elements, as we can see from the animation. And what is the speedup achievable now? Just playing on the data layout, we are able to have 3.5 better performance. But we can do more. So basically now we want the following thing. We can compute a block of 4/4 elements per thread in order to reuse the loaded values from the matrix A. But as we can see from the animation now, the problem lies on the matrix A, because every time we need a value from the matrix A, we need to load those values from different rows. So it's not cache friendly once again. We need to reshape our matrix A. Different approaches, and the approach that we are going to present basically helps to exploit better the vector capabilities of our architecture. How does it work? Basically, we split our matrix A in chunks, where each chunk is composed by 4 rows, and for each chunk, we split each chunk in blocks of 4/4 elements. We do the transposition, and we store those values. Probably it's better to see an animation in order to understand how does it work. For instance, let's take in consideration chunk 0. We split chunk 0 in block of 4/4 elements. We take block 0, we do the transposition, and we store the values. After that, we take block number 1, we do the transposition once again, and we store those values after the values of the block 0, and so on. These operations are repeated for all chunks. And now, what is the speedup achievable? Without using any tricky optimization and just playing with the data layout of our matrices, we are able to see 8 times better performance with respect to the naive implementation. Of course, one consideration could be, yes, we are able to have 8 times better performance, but we need to take in consideration the time for reshaping our matrices. And we need to take in consideration that we need at least 2 extra temporary buffer for storing the reshaped matrices. Yes, but we have experimented that with large matrices, as we have for convolutional network, just the 3% of the overall time is spent for reshaping the matrices. Moreover, the reshape of the matrix A can be merged with the image-to-call function, so we can skip the allocation of 1 extra memory buffer. The second approach that we are going to see is based on the FFT. As we know from the convolution theorem, a convolution in a spatial domain is equivalent to a scalar pointwise multiplication in the frequency domain. In particular, we need to do the FFT on the input images. We need to do the FFT on the convolution kernels. And after that, we can do the convolution in the frequency domain as a pointwise multiplication. However, in order to have, once again, an image in a spatial domain, we need to apply the inverse FFT. The most famous FFT is a radix 2 Kulittaki algorithm, which works with n power of 2, where n is equal to the number of input complex value. And how does it work? Basically, the implementation breaks the computation in a smaller and simpler DFT of size 2, and it uses a divide and conquer strategy. However, having n for exactly fitting radix 2 Kulitak algorithm, it could bring to a significant performance drop. However, for n, any factorization would be generally possible. And the generalization of the basic radix to FFT is called mixed-radix. We have experimented over 1.5 better performance than radix 2 Kulitak algorithm, also with n power of 2. With this slide, I'm going to summarize the main features behind the FFT implementation. Probably it's not enough a talk of 25 minutes for showing all the possible strategies for optimize the FFT. Basically, we use a recursive FFT in place computation, so every time the input is overwritten by the output. Each thread computes a single radix element with a floating point computation. We use a blockwise 2x2 in-place transposition, which it has 2 times better performance than the out-of-place transposition. But the main drawback behind this approach, the FFT implementation, is the out-of-place batched convolution. So when we need to do several convolution kernels in parallel, because we need to keep the frequency representation for the input images, the convolution kernels, and for the result of the convolution. With the next couple of slides, we are going to compare these two approaches. In particular, we are going to see when it is better to use the SGEMM approach and when it is better to use the FFT approach. But before showing when it is better to use, for instance, the FFT, I'd like to highlight the main drawbacks behind these two approaches. For both, we have high memory requirements. For SGEMM, due to image to call, because in particular when we have a stride lower with respect to the kernel dimension. And for the FFT, we have seen for the batched convolution. But for the FFT, we have other 2 important drawbacks. We don't have an efficient way to handle stride not equal to 1. And the other important drawback lies on the implementation of the FFT, because it could require a considerable effort to be highly optimized, because most of the optimization will be, of course, architecture-oriented, but will be as well algorithm-oriented. OK, let's do a comparison. I have reported just 2 case studies. In the first one, we have single input images, and we want to compute in parallel several convolution kernels. In particular, we want to apply 64 convolution kernels in parallel, 128 and 256. It could be, for instance, a first convolution layer of our convolution neural network. In the second case, we have 64 input images, and we have 32 convolution kernels to apply. The study is limited just to the inference, and we have the stride x and stride y equal to 1. As we can see from the comparison, the FFT results better than the SGEMM approach when we have large convolution kernels. In particular, we have experimented over 3 times better performance when we have convolution kernels bigger than 9 by 9. However, what does it happen if I have just the stride x equal to 2? Just in few cases, the FFT results better than SGEMM. And also, if we have the stride y equal to 2, basically, we don't have any benefit from the FFT. So it means that in most of the practical architecture for convolution neural network, SGEMM results the better implementation. However, if we have an architecture with large convolution kernels to apply with a very small stride, probably we need to take in consideration the FFT because it could bring to a significant speed up. We are approaching the end of this presentation, but before finishing, I'd like to emphasize the important aspect of limited numerical precision for convolution neural network. because some papers in the last couple of years have demonstrated the feasibility in using limited numerical precision for convolution neural network. And this opened an interesting computational scenario if, for instance, we had hardware accelerator, for instance, for 16-bit half floating point, because it can bring to performance boosting due to the reduced memory traffic between and to the external memory, and the possibility to dispatch fewer threads. But moreover, we could have energy saving, which is definitely important for a mobile system. And essentially, it's due to the reduced memory traffic between and to the external memory. For SGEMM, we have experimented 2 times better performance, because basically we are able to dispatch fewer threads. And now each thread computes 8x4 elements. For what concerns the FFT implementation, we are not able to double in the performance because each thread computes a single radix element. So we are not able to reduce the number of dispatched threads. But however, we can see a significant speed up also in this case, which is over 1.5 times. What is the lesson learned from this talk? Analyzing these 2 approaches, we have understood that cache-efficient data layout has a huge impact on the performance of our algorithm, also for GPU computing. Moreover, with SGEMM, we have appreciated that simple changes in a data layout can bring to dispatch fewer threads and to exploit better vector capabilities. In the end, with the previous slide, we have seen that the important role of limited numerical precision, which plays a crucial role if it is hardware accelerated. In the end, I'd like to say that the convolution calculation is definitely an embarrassing parallel task, which can be easily and efficiently accelerated on the mobile GPU by means of OpenCL. Thank you very much for your attention. I think it is question time. Yeah.
Got the mics in the room. I have one question to start with. So it sounds like there's a fair amount of interesting optimization that can be put in place if you understand kind of the microarchitecture of the platform you're going to. What kind of tool support or library support is there to kind of, for someone that's not an expert like you, to implement these kind of networks?
So basically, we have used, in our case, OpenCL. OpenCL provides also the support for half precision floating point.
Okay.
Of course, if the hardware has these capabilities.
Okay.
In this case, yes. It is not a framework for deep learning. It is a framework for massively multi-threading applications.
Okay.
But of course, it is definitely usable for seeing significant speed up in our applications.
Okay, so by OpenCL, you mean a library of OpenCL functions that already implement this kind of optimization?
These optimizations are just internally, so we have shared our results.
Okay.
So we don't have a public library with those functions.
Okay.
So it is just an internal investigation and that we'd like to share
Okay, great.
with you.
All right. Any other questions?
Hey, I have a question.
Yep.
I wonder if there are any OpenCL profiler to help us optimize the code, analyze the performance.
Profile, what do you mean?
Like some profiling tools so that we can analyze the timing for each steps and memory usage, register usage.
Yeah, definitely a good question. I can answer for my company. Basically, we have an important tool which is called Streamline, which provides definitely what you want. Basically, it says basically you can see, for instance, the number of cache misses, the memory utilization. We can see how many arithmetic instructions are emitted, for instance. Also, you can see the compute load between the CPU and the GPU. This is for us, I mean, I'm talking for ARM. So I don't know which kind of other profilers other companies have. So This is for ARM. This tool is particularly useful for this kind of application in order to analyzing the problem. Yep.
Over here, another
Yeah. Did you consider one-by-one convolutions in your work?
Sorry?
Did you consider one-by-one convolutions in your work?
No, not yet, but we are going to try as well this one, the one-by-one convolution, which is probably the future for our convolutional network, definitely.
Sure. Okay, thanks.
Yeah, thanks a lot for the question.
right over here.
Yep.
Anything over there? Okay.
Hi. Do you have any public, like academic write-ups or white papers on any of this? And also, do you plan to release any sort of open source public code or
Yeah, okay. Related to SGEMM, we have a public source code that you can try you can download, you can use for your exam. We are going to publish a blog which explains all the strategies behind SGEMM, but the code is available basically for downloading. I have reported in the references, the link to the SGEMM implementation for ARM. Yeah. Just one note that basically I mentioned that the reshape of a matrix A can be integrated in image-to-call function. In that example, we have two different kernels for reshaping matrix A and matrix B, so we didn't integrate that in image-to-call. It is a potential optimization, of course, for convolutional network. Yep. There is.
Okay. Well, that concludes the session for today. I want to thank Gianmarco.
Thank you very much.